All right, let's get started on our next video. Up until this point, um, all the motion we've discussed has been in one direction. He ran north, or then he turned around and ran south, or we threw a ball up and then it came straight back down. That's not the way the real world works. Sometimes things go off on different angles, and that's what we're going to talk about here. Not things that are traveling in straight lines, either straight north, north-south, or east-west. So here's what we call a vector. Yes. It is being represented by an arrow. Length should be proportional to the size. Yes, I'll just leave it at that. The length should be proportional to the size. So here we've got a vector headed off here, more towards the east, but it's a little bit to the north, and we need to be able to somehow write down about this vector here, so or in what direction it is. So there's two ways to do it. We could say that this thing is 20 degrees north of east. Yes, there's east, and this, so we're going to go 20 north of that. Or we might say that this is east 20 degrees towards the north. And I personally like this one here, but you pick whichever way you want. They're both equal and fine. So we're going to be using these things called vectors, which are arrows. They point in the direction that you're interested in. To solve these problems, we're going to be adding. So to add to having a bit of trouble here. To add two vectors, why does it keep that? We add them tip to tail. And that's important, and you should have that written down, taking some notes as we go here. We're going to add these two guys, tip to tail. I'm going to show you what I mean now with a little example. Here's two vectors. Say something travels 5 meters towards the east and then travels 6 meters to the south. Okay, so I've drawn my two vectors. Now I need to add these two things, so I am going to draw them tip to tail. So I'm going to do that over here. Does not matter which one I start with. Does not matter. I'm going to draw that guy. Yes. And then I am going to start the next one. At the tip of the first one, I'm going to attach the tail of the second guy. Okay. Whoops. Didn't really want to drag him over there, but it'll do for now. Yes. And so where is he? What is his actual displacement in the end? The actual displacement is this. Because displacement depends on only two things: where you start and where you end. So this is his displacement. Now, since he was traveling east and then south, I know something about this angle right here. I know that it's a 90-degree angle. I know this is 5 meters east. I know this is 6 meters south. Whoops. what I'm interested in is how far this is, and hopefully you can remember or recognize that this is just a basic math problem. This is a right-angled triangle, and I'm interested in finding this side, which is opposite the right angle. I believe we call this the hypotenuse. And so I'm going to use Pythagorean theorem. And I'm going to say that D, and I'm going to put these around it because it's a vector, and I'm not dealing with any distance or directions right now. I'm only interested in its length, so technically it's not right just to put D with the arrow. So I put these absolute value bars around it, which means to everybody, mathematicians and physicists, listen, we're only calculating the length right now. I'll deal with the direction it's in a minute. Is equal to, squared, equals 5 squared plus 6 squared. And then I do some math, I square root everything, and I get that that guy has a length of 7.8 meters. Hooray, I'm done! No, you're not done. We need to be able to say in what direction this is going. I need this angle right here. So I'm going to find that angle right there using a trigonometry identity. The two sides I currently have are adjacent and opposite, so I'm going to use tan. Tan theta equals opposite over adjacent, which is opposite here is 6 because it's opposite the theta. The adjacent side is 5. I plug that into my calculator. I use the second function, or shift tan, and I get an angle of 50.2 degrees. Same old problems coming up. Let's just say 50 degrees. Hooray, I'm done! No, you're not. You haven't actually answered the question. I have to bring both of these things together now. I would say now that D is equal to 7.8 meters, and now I have to somehow give the direction that it's traveling in. If I look back up here and go up, it's east 50 degrees towards the south. East 50 degrees towards the south. So I come down here, I go east 50 degrees south. Now I'm done. How many marks is this question worth? It's a good question. How many questions is it worth? How many marks is it worth? You would get a couple for doing this. You get a couple for doing the theta, and you get one for putting them all together. This guy is worth 5 marks. Okay. Now that's a pretty straightforward example. The next guy, maybe not so much. I'm going to draw a little line here. Somebody runs this way, then somebody runs this way. What is the final velocity? Blue, that, get my pen out. This is the guy that I'm interested in right here now. If this guy here is 6 meters, if this angle is 40, which seems pretty ridiculous. I'm just looking at my my example here. Yeah, 40. I don't know why. Diagram is way off. Here's theta, and this side is 7 meters. Now I don't have a right angle triangle. And that makes me sad because I can't use Pythagorean Theorem. But there's other tricks in math. Math is full of tricks. And in this question, I can use the cosine law. If I'm going to call this d, I can say d squared equals 6 squared plus 7 squared minus 2, 6 times 7, and this is the cosine law, cos 40 degrees. And I can eventually work this down and figure out that the displacement vector has a length of 4.5 meters. Just like that. Now I still need this angle. I've got 40. I can then use, wait a second here, let me write down here that this is the cosine law. Right? Then I can use the sine law, which I'm hoping you remember from math, which would tell me that the sine of theta divided by the side across from it, which is 7, is equal to, now this is the pair I know. Whoa. This is the pair I know, is equal to the sine of 40 degrees over 4.5. Just don't know why it keeps doing this. And I can figure out theta using some cross multiplication. I would do 7 times the sine of 40 divided by 4.5 is the sine of theta. Eventually I work this down and I get theta, and you should try this on your own. Don't just sit and watch. See, theta is about 82 degrees. Okay. So here my answer would be 4.5 meters. Now square brackets, I'm going to go east 82 degrees towards the north. Now I think technically you should never have an angle bigger than 45. You should switch your east and north around, but I don't really mind it. It's not a big problem for me. Okay. So this is how two examples of how we can do motion questions in 2D. Now both of these were questions that had to do with displacement, and I'm using meters were my units. I can also do the same question with velocities. Doesn't matter. Everything stays the same except for the units that you're working in. The process stays exactly the same. Thank you. And now you should try some questions, sample questions from the textbook.